Okay, microphone active, so let us go to Notability and so let us do this exercise. We will discuss this exercise. It says compute the work made by the force field F x, y, z is equal to minus y cube I plus x cube j minus z cube k. Along the ellipse gamma intersection, so this ellipse is described as the intersection between the cylinder x square plus y square equal to 1, so it is based on the circle of radius 1 centered at the origin, the plane xy, and the plane x plus z equal to 3. This ellipse is oriented counterclockwise when seen from above. So we probably need a picture. I'm not very strong in pictures, but I'll try to do it. So we have this, as usual, Cartesian axis. One, two, three. So we have x, y, z. So here we have first the cylinder. The cylinder, here we have a circle, which is x squared plus y squared equal to 1. Z does not appear in this equation, so this is the cylinder. Okay. Then, so the cylinder with the axis parallel to the z axis. Then we have the plane x plus z is equal to 3, which means that if you look at it in the plane xz, it passes from these points 3 and 3. And so here it is. So you see this line, this is in the plane xz, and then you have to extend it along the y direction. This is the plane, because y does not appear here. So of course I'm not very good in doing pictures, but the idea is that from the intersection of this cylinder and the plane is not parallel to the cylinder, to the cylinder, so it's not orthogonal to the axis of the cylinder, so the intersection is not a circle, but it is an ellipse. try to do this picture by yourself much better than I did here, but what you find at the end is something like that. This is gamma. Gamma has to be oriented counterclockwise when seen from above, so, and this is the correct orientation you have on gamma. Okay? So, now we want to apply Stokes' theorem. And the first step is choose a surface which is delimited by gamma. And so the natural surface to be chosen here, perhaps the first idea, is to choose the surface on the plane x plus z equal to 3. And this is the surface. It is a planar curve, so we can choose the plane here, and let me choose another color, and the normal vector will be this one, because owing to the rule of the right hand, here you see that this vector sees the circulation going counterclockwise as required. Good. So, first of all, we apply Stokes' theorem and to this aim we choose the surface sigma delimited by the curve gamma on the plane x plus z equal to 3. So this is very important, and let us describe this surface in a perhaps more efficient way. So sigma will be x, y, z in R3 such that x squared plus y squared is not larger than 1 and z is equal to 3 minus x. So this is exactly the surface here. Okay, and we have to choose a parameterization, and the parameterization is very simple. And as a parameterization, here notice that this equation is given as a graph. The graph of the function 3 minus x in the three-dimensional space. So it is quite natural, as always done when we have z equal to some function of x and y, even though here y does not appear, to use this parameterization, to use r it's a function of the two parameters u and v is equal to u I plus v j plus 3 minus u k, and of course u and v must fulfill this constraint: x squared plus y squared, sorry, that's what we call them, 1 This translates to u squared plus v squared less or equal than 1. And this is our D. Okay, in the space of the parameter, we are really on the circle. Okay, and so let us see whether the orientation is the correct one. So, of course, we have to compute dr du vector dr dv, and this is equal, so dr du is I minus k vector j, so I vector j is k vector j is minus I, but there is a minus in front, so it is k plus I. Okay? And since the coefficient of k is positive, then we see that n, so this dr du times dr dv is oriented upwards. So, by definition of gamma, of the orientation of gamma, it sees gamma as being oriented counterclockwise. As oriented counterclockwise, so it is correct. Okay, this simply means that this is really the end that we chose, and since we chose the orientation seen as counterclockwise from above, this vector points above, so we are done. Good. Now we have to compute the curl of the field. So we have nabla vector f, nabla vector f, nabla cross f, is the determinant of the strange matrix. Here we have the unitary vectors e, j, k. Then we have the field minus y cube, x cube, minus z cube. Oh, sorry. This is the last row. Okay, this is the last row, and I took the j, and here you have d with respect to x, dy, dz. So noted that here, for the component I, you have dy minus z cube is 0, minus the zx cube, so you don't have component I. For the component j, you have dx minus z cube is 0, dy minus y cube is 0, And here, for the component k, you just have the component k of this curl, is 3x squared plus 3y squared. And now the flux. At the end, you have to compute the flux, and so the circulation on gamma, this is equal to, we use Stokes, and here you have sigma, double integral on sigma of curl of f scalar n d sigma. Here I want to clarify a point which is always ambiguous, because here the unitary vector n is dr du cross dr dv, but it has to be normalized, so it is dr du cross dr dv. But then the sigma is, of course, du dv, and then the element of area, which is again dr du cross dr dv in modulus. So these two cancels. And so the expression you have to remember is the following. This is the double integral on sigma of curl of f dot dr du cross dr dv du dv. And so to be rigorous, this is not an integral on sigma, which is the real surface, but it is in the surface of the parameters, which is d. And now just to replace what you found here, so double integral in d of 3u squared plus 3v squared k dot, it was I plus k du dv, and this is equal to the integral on d, which is u squared plus v squared less or equal than 1 of 3 u squared plus v squared du dv. This is quite easy to do in polar coordinates. I don't want to bother you with the definition of polar coordinates. Of course, you have the integral 0 to pi of d theta, and the integral from 0 to 1 of rho d rho, and then you have 3 rho squared. So you have, from the first integral, you have 2 pi, and here you have to integrate 3 rho cube, and this is like 3 rho to the 4th power divided by 4 between 0 and 1. And so you have 3 over 2 pi. This is by applying Stokes' theorem. Just to verify the result, let us do it by the usual parameterization, so without Stokes' theorem. We parameterize as so R of t is equal to cos t I plus sin t j plus 3 minus cos t k, the usual parameterization, and then we have that field times r dot in dt is equal to the integram between 0 and 2 pi, and here you have minus sine cube of t then cos cube t, and then 3 minus 3 minus cos cube times what? The velocity, which is minus sine t, cosine of t, sine of t. dt. This is an extremely long and boring integral. I'll just give you the final result, and nothing that here you have what you gain at the end is just the integral between 0 and 2 pi of sine 4 of t plus cos 4 of t in dt simply why if you integrate the others you always have a combination of cosine and sine which give you an integral 0 on 0 to pi. Please verify it. Then you apply the usual trigonometric formula that we applied in previous exercise, and so you here write 1 minus cosine 2t divided to the square plus, and this is sine to the fourth, plus 1 plus cosine 2t to the square divided by 2. This is in dt. And then you apply again the formulas and you end up with 0 to pi 1/2 plus 1 plus cosine of 4t divided by 4 in dt. And so at the end, here you just have no contribution from the cosine, so you just have 1/2 plus 1/4, which is 3/4 times 2 pi, and this is equal to 3/2 pi. Here, I skipped many passages. Try to do it slowly, and you will see that this is very long with all passages. This computation is much longer. Okay, see you next time for Divergence Theorem, and then the program is finished. So before doing Divergence Theorem, I would like to give you a sort of argument for a very formal proof of Stokes theorem. But it is very quick. Bye bye.